Okay. We continue on. Remember in the last unit, we did 4 things with proportions. We found a confidence interval for one proportion. We did a hypothesis test for one proportion. We did a confidence interval for a difference between 2 proportions. And we did a hypothesis test for a difference between 2 proportions. And we're doing the same thing with the first 4 lessons in this unit, except it's means now, okay, instead of proportions. So there's slightly different formulas that you will get, okay? So we've done a confidence interval for one mean. We've done a hypothesis test for one mean. And now we're doing a confidence interval for a difference between 2 means. So here's the example, okay? College graduates make more money than high school graduates, even when accounting for the extra cost of college. However, it's unclear if a college degree actually causes higher earnings. Perhaps there could be some other factor at play, such that people colleges select, or highly motivated people, would have made much more money anyway, regardless of whether or not they went to college. So that's one that could be a possible confounding variable. So the question is, does college have a causal impact on earnings? Does college actually cause an increase in earnings? So a Florida college, a study of a Florida college by a Yale economist, don't worry about the type of analysis they did. That's beyond what we do in this course. But basically, it was sort of a semi-experimental method. So all we need to know that it was experimental, because that will help us answer a couple of questions. So it was done to explore whether college had a causal impact on wages. Okay. So what we're going to do is a 2-sample, because it's 2 means, T interval. Remember, means we use T, not normal or Z. So the study compared students whose high school GPAs were just above and just below the 3.0 GPA cutoff for standard admission to this Florida university. The groups were as good as randomly assigned if they are similar, and if the students/teachers could not purposefully manipulate GPAs to meet the cutoff. Okay, and the study found that these assumptions hold true. So we've got 2 groups. Okay, and for purposes here, we consider them sort of randomly assigned. We've got a group that are just below the cutoff, so they don't qualify for admission. And we've got a group that are just above the cutoff, so they do qualify for admission. And here's some numbers. Okay, here's the results. So the mean income of the blue group went to college, $35,764. For the group that didn't get accepted to this college, $28,964. You can see the standard deviation. We need that for the sample. And the sample sizes for each. Notice the college group is slightly higher. Okay. So what we want to do is we want to determine, okay, what's the difference in the sample means? So all we have to do to calculate this, our sample difference is take the mean from the college minus the mean from the high school, the sample mean. So that's going to be 35,764 minus 28,964, which gives us a positive number of 6,800. So right now, just doing a very simple calculation. Does this lean towards saying that, yeah, college does cause an increase in earnings? Yeah, because this difference is positive. Okay, but We can't be absolutely sure because we may have got a weird sample. Okay? We may have just got this by chance alone. Maybe another sample we do for both college and high school gives us a negative amount. We don't know. So the usual explanation. Because the mean difference is positive, is positive. It suggests college causes an increase in earnings. However, we don't know if the difference in the sample occurred by chance. Remember, that's referred to as sampling variability. Different samples will produce different results. So we need to do a little bit more study, a little bit more statistical analysis. And that means sort of taking many, many samples, running the simulation, and seeing what happens from that. So once again, what we're going to do with these is we're going to do it the long way, okay? And then we're going to do it the shorter way using the 4-step process and one graphing calculator function. So what we're asked to do is construct and interpret a 95% confidence interval for the difference in mean incomes, okay, for those who do attend and don't attend college, and then comment on whether this interval provides convincing evidence that college had a real effect on wages. So remember when we did a confidence interval for one mean, okay, the average of all the sample means we took was the average of all the sample means is the same as our sample difference. Standard error, okay, we calculate by using this, and you will get this formula. Okay, you will always get that formula. And notice that we take the standard deviation of college divided by the sample size of college plus. We don't subtract, and we talked about that before when we talked about variance, because standard error is spread. And if we want to find the total that's spread out, okay, it doesn't matter whether we're subtracting or adding, we always add to get the spread. So in this case, we've got, what do I have here? I got a completely different thing. So here, our sample difference was $6,800. We calculated that previously. Okay, that's going to represent the difference in the true means. Difference in means. the standard error for the difference between these two is going to be the standard deviation of college squared. Notice it says squared. Okay, so that was 27,147 squared divided the sample size that went to college, 202, plus the standard deviation of the sample that was high school only, squared, divided by that sample size, which is a little less than 190. So when we calculate these, once again, substitute 6,800. Then when we do the standard error calculation, using the sample results, you get approximately 2,484. Okay, so we'll start our graph here. And remember, this is a t-distribution. Looks like a normal, but it's slightly different, slightly wider than a normal distribution, depending on the degrees of freedom. So we're going to have to calculate degrees of freedom as well. Anyway, we've got our difference in the two sample means there, 6,800. Okay. We've got our standard errors, which would be, I guess I have to use that. I don't have these calculations. So we would do 6,800 plus 2,484 plus 2,484 plus 2,484. 6,800 plus 2,484 gives us 9,284 plus another 2,484 gives us 11,768 over there. Really, I don't need to know the third one because 95% confidence is a little less than 2 standard deviations. I mean, I can put them in 2,484 and I get 14,252. And then 6,800 minus 2,484, 4,316 minus 2,484, 1,632. And then this last one finally gets us into the negatives. Negative 652. Okay. And remember, this represents the difference in sample means. So it represents okay, so we have to figure out for a 95% confidence interval, how many standard deviations are we away from the mean? And remember, we said earlier on in the year, it was generally 2, but with Z intervals, we saw that it was 1.96. With a T interval, it's going to be a little bit different because T intervals are slightly wider. So how do we calculate these values here? Well, first of all, we have to get the degrees of freedom. And the degrees of freedom when we've got 2 sample means take the smaller one, -1. Take the smaller sample size. So in our case, it would be 190 -1, which is 189. That's pretty high degrees of freedom, which means it's going to be pretty close to a normal. And then to find at 95%, to find the critical value for t, I've got to do inverse t on my graphing calculator, and I will be asked for the area, which is 0.025, because remember, if this is 95% in here, these two are 5%, each one is 2.5%. So what I can do is I can either find this value or this value, and I'm going to find this value. Okay. So, which means it's going to give me a number somewhere around there. Or no, sorry, not somewhere around there. Tell me the number of standard errors. And the degrees of freedom is 189. So when you do that on your graphing calculator, you're going to get approximately 1.97. Okay. So that means that we are 1.97 standard errors away to cover 95%. So it'd be from here to here, it would be 1.97 standard errors, right? So this is 1.97 standard errors. And we know each standard error is 2484, so we can calculate that result. And then here to here would be 1.97 standard errors. So we can actually figure out these results. Remember, this will give us our confidence interval. Okay? We know that this is going to be a little less than 11, because we know 2 standard deviations away is 11,768. 1.97 is going to be a little less. Here, 1.97 standard deviations here. Here's 2 at 1832. It's going to be a little bit greater. Okay, so we can tell that from the graph. So to get the actual confidence interval, remember the confidence interval represents the point estimate plus or minus the critical value, which is the number of standard deviations away, or standard errors away, times whatever the standard error is. So our point estimate is the difference between the two, which represents the center of the t distribution, 6,800, plus or minus, we're 1.97 standard errors away, and each standard error is 2484. So we have to do 6,800 minus 1.97 times 2484. That's our low value in the interval. And then we have to do 6,800 plus 1.97 times 2484. And that's our highest value. So we get 1906, comma, 11,693. And of course, those are dollar values. Okay, which makes sense because, like I said, here it was going to be slightly above 1832, which it is. Here it was going to be slightly below 11,768, which it is. So we would say we are confident, or sorry, we are 95% confident the interval, and then I'm going to put the dollar signs in because it is dollar signs in this question, $1,906 all the way to $11,693 represents the true difference in mean incomes of college and high school students. And then we have one more question to answer because it did say up top. Comment on whether the interval provides convincing evidence that college had a real effect on wages. Did it? Why? Why can we say for sure that it had a real impact? If there was no impact, what would the difference be? Zero. But all the differences are positive in our confidence interval. So it must have. Okay. So because zero is not in our interval, which means no difference, we have convincing evidence college has, what did I say here? College has a real effect on wages. So again, that's if we did it the long way using that confidence interval formula. And then getting the P estimate from the question, getting the standard error from a certain formula, getting the critical value by doing inverse T. Okay, but again, we have a graphing calculator function that will do all of that for us. So let's revisit the question on how we would do it using 4 steps. And hopefully you are familiar with these right now, or by now. So, state, well, we're constructing a 95% confidence. Oh. Or the true mean of college wages, I'll say, minus the true mean of high school wages. So where we would say this equals the true mean of, I'll say, wages with college. And U8S equals true mean of wages with high school. And then how are we going to go about doing this? What's the plan? Well, the plan is, this is where we say we are constructing, calculating, we're constructing a two sample, because we're dealing with a difference here. And because it's means, and because it's a confidence interval, we're doing a t interval. For this, the difference between wages with college and wages with high school. And then, of course, yeah. Random. 10%. And remember, because we're dealing with means, not large counts, large sample, that's where it has to be greater than or equal to 30. Okay. Did it say anywhere at the beginning that it was random? Yes, it said, I believe in quotes, it said as good as random. That's good enough for us. That means we can use the point estimate. The 10% allows us to use the standard error formula. Okay, remember, has to be 10% than the population size, unless it's an experiment, which it is. It did say it was like a quasi-experiment, which basically qualifies. So we don't need to worry about calculating the 10%. We don't need to verify. So that means we can use that standard error formula, even though the graphing calculator function is going to do it for us. And the large sample, we have two samples. Remember, the first sample has to be greater than or equal to 30. The second sample has to be greater than or equal to 30, which they both are. So we got 202 for the first sample, for the college samples, and 190. That's good, that's good, that's good. Now we can go on to the graphing calculator. Okay. And here's what we do. And we're going to have to talk about some point, because by the time we finish Unit 8, we're going to have 8 different graphing calculator functions. So we got to remember which one is which. Okay. This one, we're doing a 2-sample t interval. Okay. Which makes sense. If it was proportions, we do a 2-sample z interval. So with your graphing calculator, under Stat, scroll over to Tests, get over to 2-sample t interval, which is 0. And then you're asked for a bunch of information. Okay, and remember, you want the input stats highlighted. Otherwise, it will ask you for other information that you can't use. So the first thing we are asked for is the mean of the first one, which for us is the college sample mean. So the college sample mean was 35,764. The sample standard deviation was from the first page 27,147. The sample size for the first one, which we call college, is 202. And now we move on to the high school mean sample. The mean for the high school income was 28,964. The standard deviation for the high school example was 21,899. And I'm getting all these from the front page, from the first page. And the sample size for the high school group was 190. And finally, the confidence level we are asked is 95% or 0.95. So if we enter all those values, 35,764, 27,147, 202 for the sample size of college, 28,964 for the mean income for high school, 21,899 for the standard deviation of high school, 190 for the sample size, confidence level, and pooled, no. And then just go to calculate. And we can see we're pretty close to when we did it the long way. We got 1915.1. All the way up to 11,685. What did we get for the other one? It was 1906. So a little bit less when we did it the long way to 11,680, 693. And it's not going to be like this one to me is more accurate. Okay, because remember in the previous one we did some rounding. Like when we calculated the standard error, we did some rounding. So that's going to change the answer. This method would do less rounding, would be more accurate, less rounding. And then finally conclude, and I'm just going to put same conclusion as when we did it the long way. Like on the previous 2 pages ago, it's the same thing. We are 95% confident. The confidence interval this in dollars to this in dollars represents or captures the true mean difference between college, mean incomes with college and mean incomes with okay. And then you would do the same thing with convincing evidence because 0 is not in our interval. We have convincing evidence that going to college does cause an increase in wages. Okay.